I already see that there are distribuati in the audience, so if you don't know who they are watching you. Well, the talk is called What We Talk About When We Talk About Distributed Systems. You may wonder why I chose these horrendous colors. It's because this talk is also called Distributed System for the IKEA family, or IKEA family. So I tried to adapt to the Swedish mood, let's say. I'm even using Verdana from the font. And I went specifically to a website to choose IKEA yellow and IKEA blue. Anyway, so distributed systems. Definition by Leslie Lamport, you probably heard it many times, even attributed to different kind of people, probably Einstein, who knows. A distributed system is one in which the failure of a computer you did not even know it existed can render your own computer unusable. It's basically when Facebook goes down, you cannot use the internet anymore because of all these like buttons, they don't let you load your website. Or when GitHub goes down, we cannot program anymore. That's basically how to make a distributed system centralized. That's what we did with GitHub. But more seriously, the idea of the talk is that when we try to learn distributed system, that's my case currently, there is a lot of jargon. There is a lot of definitions, a lot of terms, words that they might mean what you think they mean or not. And it's a very specific definitions on each of them that will let you understand why a theorem means something or why an impossibility result means something else. So yeah, that's jargon defined by Google. Special words or expressions that are used by a particular profession or group and are difficult for others to understand. That's what I feel about the distributed systems literature. So, as a definition, that this is from a book by Michel Reynal, a French distributed systems researcher. He says that basically you have many nodes trying to solve a problem, or many processes. They have partial knowledge of the whole system, and they have uncertainty. They have no idea what's going on the other side, and is the other node alive or not? You don't know in a distributed system. That's basically what defines how computation works here, is uncertainty. We don't know what's going on, basically, which is quite hard in computer science when we are used to everything be so deterministic. And I found that it's a very deep rabbit hole. There are a lot of things to read. There are blogs out there telling you, read this paper, read the FLP, read the original CAP paper, or blah, blah, blah. I have no idea if I should do that. So which papers to read? There is the FLP paper, the Paxos paper, the time clocks that if you don't cite this paper, you are kicked out of the distributed system community. You have to quote that paper in your paper, basically. This is the ZAB, the Zookeeper paper from Yahoo and so on. And this is the Raft. If you are a hipster of distributed systems, you need to know Raft, basically. The Paxos is too old already. So yeah, we have all these things, and what do I need to read? Why should I read about Raft or FLP, the first one, the impossibility result or whatever? I don't know. And that was my problem, and still is kind of my problem, that there are so many things and it's hard to focus and to know if, let's say, I work for RabbitMQ, I want to improve how RabbitMQ is doing mirroring. Should I read about Raft, or should I read about Paxos, or should I learn Erlang that Joe is here, because Erlang solves every distributed system problem, right? There are no more problems, you just use Erlang, right? So what to do? Then there are books. There are a ton of them. These are some of my library that I managed to collect over the years. Some of them, they don't even talk about distributed system, like this one. Sorry for the camera. This one called Programming Distributed Systems. Let me tell you something. Spoiler alert. It's not about programming distributed systems. It's a book about the actor model, the pi calculus, and all ways of writing or specifying distributed systems. But I bought that book and say, wow, I'm going to learn about distributed systems and fail, get out. No, it's a really good book if you need to learn about these formalisms. But it's not one if you need to practically implement something. I'm sorry for Mr. Varela that I gave him this review, but anyway. And just in the second one, the art of multiprocessor programming, this is very important. Sometimes people confuse multiprocessor programming with distributed systems and want to put everything into the same box. It's not the same. There are related problems because you have states in many processors, but the algorithms and the literature is not the same. So for me, it was quite important to realize that yeah, maybe you can implement a concurrent queue, and there are many problems that they solve that you could later apply on a concurrent distributed queue or whatever, but the literature is not the same or targeting the same exact problem. So be careful. And then there is the why, like, why? Why should you learn and do all these things and waste all this time? We don't have all the time in the world, so should I just grab, let's say, Bashos, React Ensemble and be happy in my life, or try to know what's going on behind and so on? So continuing with the IKEA theme, this is from somewhere. And yeah, that's how you end up when you start learning about distributed systems. I guess what that means in Swedish is not so polite, but yeah, don't kick me out, please. Anyway, I'm just quoting, right? So the problem. The problem of learning about distributed systems is there are different models on which papers, books, results, theorems apply. That's the main thing. I hope this is new for you as it was for me. Again, probably it's the description and the talk on the website. This talk is, in certain terms, is beginner level. But it's beginner level in quite a complex problem as distributed system. So I hope you get something out of it. If you know this already, I'm sorry. So one model is the timing model. Algorithms, they define something about what time means for them. Then there is the interprocess communication used by these algorithms. And there are failure modes. So algorithms in distributed systems, they combine these things, and based on what they take from each of them, you have a theorem or an impossibility result, and so on. Timing model. There is the synchronous model, where algorithms, they usually are executing steps, and it's very well known in this model how long they take to execute that particular step. Either receive a message from a message queue, put a message on the message queue, implement a step of the algorithm like traverse a tree, whatever they're doing, but that's very known bounds on how long it takes to execute that step. And the same in the message passing. In this model, it's known how long it takes for a message to go from one node to the other node. You know that if after, let's say, 5 seconds, the other node didn't reply, you know it's down, it's failed, and you can detect that. Where on the asynchronous model, that's should be called the living la vida loca model, actually, because there are no guarantees about anything. There is no guarantees how long a process will take to run a step. You don't know how long it will take to receive a message, to put a message on the queue, how long the message takes going through the network. You don't have any of these guarantees. The scheduling of an algorithm could be fair, could be unfair. Your process never gets to be scheduled, and you don't know anything. So that's the asynchronous model. Again, maybe if we, like now in Node.js, I mean, in the current programming world, you can say asynchronous, use Node, synchronous, Java, whatever. I mean, I'm making a very stupid example, but point is, synchronous means one specific thing, and asynchronous also. It's not like, yeah, I've seen async before. In Node, you do async all the time. No, it's not that. It means something else in this context. And then there is the semi-synchronous model. Because both of the top ones, they are kind of unrealistic. And except probably on real-time computing, you don't have a synchronous model where you know exactly what boundaries you have for computation and so on. And on the asynchronous model, I mean, if you go to an ATM and it doesn't give you the money at some point, you stop and go to the next ATM. I mean, you're not like going to wait forever till somebody decides to schedule your ATM, for example. And the same happens, a user using RabbitMQ, they expect that we reply your message after some time and so on. So they are very nice theoretical models, but they need a semi-synchronous one where some boundaries are put in between to do things. This book by Nancy Lynch that I had in one of these links has algorithms. It's very well organized, the book, because it has algorithms for the first model, for the second model, and so on. So you are not guessing what you're learning. Interprocess communication is pretty simple. There is either message passing or shared memory. Most algorithms, I would say, are about message passing systems. And yeah, you need to know how communication is done and what message passing means. Are the channels inventing messages out of thin air, or they are reliable and they don't come up with new messages? Do they reorder messages? Are there FIFO channels, random channel, whatever? In all these things, they define very specifically what this algorithm covers under that particular model. And finally, this is also quite important, are the failure modes that a process can have for the algorithm to be correct or for the proof to mean something. Crash stop model, very simple. If the process crashes, it's gone. It's not going to keep doing computations. It's not going to come back or anything. It's gone. Crash recovery, the process can come back and join the system. For example, in a crash stop model, if the process, let's say the machine recovers and joins the group later, that's a different process, completely different. In the crash recovery, it's still considered the same. Then a process can do omission faults. That means it may omit to reply to a message or to receive a message. Depending on the kind of omissions that the algorithm supports is what can be done. For example, a process that is managing to receive messages but is omitting to reply, we can assume that that process has a state up to date to what's going on the algorithm. So we can trust this as a replica, let's say, that kind of got everything that should be in the system. But we have no idea what it did. We are not sure if it did it, but at least data is there somehow. Then there is the arbitrary failures mode, Byzantine. This is quite interesting. It works like this. Excuse me, you on the first row. What's your name? Yeah. He just told me that he's called Carlos. What's your name? He said he's Leandro. That's arbitrary failures mode. It's like a process that will do whatever it wants. It can reply exactly what it was said to make us believe it's behaving correctly, behind the scenes doing the opposite thing, or it can give any kind of answer. It's doing replication and it's saying, this machine here told me that the register has value 10, but the machine told them it's 5 or whatever. So Byzantine. You don't want to deal with that. But there are algorithms for this. And the thing is, if you handle Byzantine failures, then the algorithm is supposed to handle all the others. So this is like a hierarchy of failures. We will see why this is important soon. Then another concept in algorithms is liveness and safety. There's a paper about this, where safety basically says something bad never happens. Cool. So what does it mean? An algorithm will say we are using, I think it's called reliable channels. And if the algorithm assumes there are reliable channels, it means messages are not going to be invented out of thin air. That's the safety property of the algorithm. It's telling you that. Or if you have a first in, first out queue, the queue will always take the first item and give that came into the queue and returns that. It won't return items out of order, something like this, or that particular order. And liveness is a good thing eventually happens. This is hope, basically. And a destination process eventually delivers a message, which, by the way, delivers means something particularly in distributed system. Usually, if I think about delivering, I think that deliver this cup of water to him, then I'm delivering. But actually, in distributed system, this is my message box. When a process delivers a message, it means it grabs a message from the message box and does some use of that message. That usually in the literature what delivers means too. So basically, at some point, the process will grab a message from the inbox. So having these models, let's take a look at what FLP is. FLP is called like that because the authors of this paper are Fisher, Lynch, and Patterson. The paper is called Impossibility of Distributed Consensus with One Faulty Process. This was, as far as I understand, a problem that was heavily debated on the 80s. What happens if a process crashes? Can we achieve consensus? Can we not? And so on. The abstract goes, the consensus problems involves an asynchronous system of processes, some of which may be unreliable. The problem is for the reliable process to agree on a binary value. We show that every protocol for this problem has a possibility of non-termination, even with only one faulty process. And so on, and keeps going. From my point of view, if I don't have this previous knowledge of models and so on, I have no idea what guarantees or what this thing is trying to prove. So it goes somewhere. In this paper, we show the surprising result that no completely asynchronous consensus protocol can tolerate even a single unannounced process death, and they don't consider Byzantine failures and whatnot. So we know the system is completely asynchronous. This means that there might be an execution where a process never gets scheduled, for example, or we never get a reply from another process. And why this is important? If you need to decide between people what to do, and some of your friends never replies to you, you cannot achieve consensus deciding on a value. And in an asynchronous system, you have no idea if the other process is not replying to you, or the other process is dead, for example. There is no way to actually determine that just in these settings. So they say, nevertheless, even with these assumptions, the stopping of a single process at an inappropriate time can cause any distributed commit protocol to fail to reach agreement. Thus, the important problem has no robust solution without further assumptions about the computer environment or still greater restriction on the kind of failures to be tolerated. Crucial to our proof is that processing is completely asynchronous. That is, we make no assumption about the relative speeds of processes, nor about the delayed time in delivering a message. We also assume that processes do not have access to synchronized clocks. Algorithm based on timeout, for example, cannot be used to solve that, and so on, and so on, and so on. And they keep explaining what the model is, why it's strong, and so on. So, before I go into the consensus thing, why this is important and what are they trying to tell us? Under all those constraints and assumptions, arriving to consensus, that we will see what it is soon, is not possible. What it means to us is like, if we have one crashing process, we are not going to achieve consensus under those settings. So tomorrow, when you go home and you try to implement your own consensus algorithm, please don't. I've seen projects that do that. I don't want to give names, but you can guess on which one is it. I don't know. If you are naive enough to think that you can solve these things without reading the theory, you will probably obviate the FLP result, which means you will try hitting your head against a wall to solve okay, but this process failed. Maybe I put a timeout, and then maybe I do this, and then I do that, and you will always be chasing your tail because there is no solution. There is a proof that there is no solution in the most weak of the things, which is only process crashes. If you go down that hierarchy, it's even worse. That's the takeout. So what's consensus anyway? The consensus problem is a paradigm of agreement problems. So it's not just one thing. There are many agreement problems which are called consensus, to agree on a value. For example, if you need have a distributed database, they need to agree if they commit data or not to the hard drive. That's a consensus problem. All these replicas need to agree if that value needs to be written. If you are delivering messages and you want to do like atomic broadcast when they have to respect some order and every process in the group receives the message, they have to agree that they receive that message or deliver that message. So what are the properties of consensus? Or uniform consensus, sorry. C termination is called the first one, which means that every correct process eventually decides on some value. Then there is validity, which means that if a process decides V, then V, that value was proposed by some process. You cannot come with a value out of thin air. Some process based on the state since the algorithm started executing, and all the states that was taken reached to some state, whatever that is. Like in my case, let's say, how old are you? I'm 33. So that is my current state. I cannot come up with some random value that I don't know where I got it from. And when I have that value, that if I decide on that value and everybody decide that I'm 33, somebody proposed that I'm 33, let's say. Not just like people coming up with ideas about what my age might be. Agreement, it means that if processes are correct, they don't decide a different value. If they agree that I'm 33 years old, everybody has the same idea. Maybe my mom has a different thing, but I don't know. Like, you may find this funny, but in Uruguay, back in like 100 years ago, to register yourself, you have to grab a horse and go somewhere. And so my grandfather discovered, after all the tales he was telling, like, you know, when I met that guy and we went to school and we did blah, blah, he was 1 year older, actually, than when he was registered, because nobody in his family managed to get to the civil registry on time. I don't know. Anyway, the uniform consensus. So without this, it's just consensus. Uniform consensus means not two correct processes, whether they are correct or not, decide differently. So the difference here, everybody decides the same. Only correct processes decide the same. Then, when do we need consensus? A set of processes have to agree to take a common action, like atomic broadcast or, for example, group membership. Atomic broadcast. Correct processes deliver the same set of messages in the same order. That's the problem that this is trying to solve. You need consensus to achieve that. Oops. So FLP tell us that if consensus cannot be achieved, then atomic broadcast or group membership cannot be achieved either. I've seen also people trying to do like atomic broadcast, for example, or group membership. But at the end of the day, that's a consensus problem. So if in your current system settings, consensus cannot be solved, the other thing cannot be solved either. No matter how smart you are and how many PhD you got from the university, you're not going to solve that. That's very important. So we pack our bags and go, like some people did already. I don't know what's with my talk. Nothing to see here. Like, okay, we cannot do anything besides probably using Erlang that doesn't have this problem. No. There is a very interesting paper by Markos Aguilera. I think he was a researcher at Microsoft. The main problem with this paper is that when he left Microsoft, his paper disappeared from the net. So if you have enough money to buy Springer books, you can read this paper. If you are not that kind of person, then I'm sorry. In my case, I think I made my company pay for it. So anyway, he says that when you get into reading consensus research, there are many misunderstandings, and FLP is one of them. FLP is not an impossibility result as the halting problem. That in this case, for a completely asynchronous system where the scheduling of processes can be completely unfair, it may happen that you have that problem. But it's not that, I think in the Paxos literature, they say that you can reach agreement as soon as you have a stable system for long enough, for example. They say that. It's like kind of hoping for good, but yeah, that's some things. And it's really good to read that thing and see what it means, actually. It doesn't mean that you are never going to reach consensus. No, that's not the case. Why? Because there are failure detectors. What's a failure detector according to the literature? There is a whole thing, paper there defining them. They are external processes. They provide information about suspected processes. So they are like the police saying that guys may be misbehaving. And they have a property where crash processes are detected. That's the completeness property. So let me see. And accuracy. That means that if a process is correct, it's never suspected. So I have a question. I don't expect you to answer, and I don't want you to because we don't have time. But the question is, completeness, crashed processes are detected. If you have a complete asynchronous system, how are you going to solve this problem when you have no idea if the other process is replying or not, or it's just, I don't know, taking a siesta like we do in South America, or what? And the same with the correct processes are never suspected. You give a timeout of 1 minute, you don't get a reply, you are going to mark the student as not coming into your class, and then suddenly they enter. So your accuracy went out of the window. As we like to say, rub some perfect failure detector on it. If you have this problem, you start rubbing this until you are done, let's say. Perfect failure detector. This is from a book, and it says you have a perfect failure detector with an instance P. And this algorithm will give an indication to whoever subscribed that detected some process P as crashed. One of the properties of the perfect failure detector is that it has strong completeness. It means that eventually every process that has crashed is permanently detected by every correct process. And accuracy, or strong accuracy, if a process P is detected by any process, then P has crashed. So that's a perfect failure detector. It will give you the properties you expect. Question is this completely useless? Why do I care about a perfect failure detector that I'm not going to implement ever on an asynchronous system? It's really useful because it's telling us these things, you only get them on those, like, even in this case, sorry, it's on a synchronous system because you know what's going on, sorry. And I think you need to have perfect channels is another abstraction this uses, that never is a message lost and never is a message reorder, and like, there are a lot of constraints. So at least you know, if you are trying to solve this problem of accuracy or completeness, I'm sorry, you can't. Because unless you have this perfect world, then this is not achievable. So again, you are super smart, you don't read papers, you jump directly to code and you wing your way with your keyboard, like this hacker man on this Swedish movie, I think it is, the Kung Fu something, Kung Fury, sorry. I guess everybody in Sweden knows Kung Fury. Yeah, unless you're a hacker man, you're not going to solve this. So there are the eventually accurate failure detectors. Eventually, every process that crashes is permanently suspected by every correct process. And there is a weak accuracy that there is a time after which some correct process is never suspected by all the other correct processes. So maybe we think that process is not working. Okay, it replied to us, back to us. It's actually, it wasn't failing, let's say. That's a paper explaining all these failure detectors. And there is this one other also, sorry. unreliable failure detectors for reliable distributed systems. Based on FLP, they came out with all these solutions to solve the FLP problem and to achieve consensus. For example, here it says, we prove that consensus and atomic broadcasts are reducible to each other in a synchronous system with class flares, blah, 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 blah. You can read that at some point. But they can solve that using failure detectors. And failure detectors, they have there's a very deep theory about what each of them allow you to do, on which system, and so on. I think this is the paper describing each class of failure detectors. So why do you care about that? There are some failure detectors that are really powerful, of course, harder to implement. Don't invest time on implementing a failure detector that is maybe too much for your sorry. There is maybe too much for the problem you're trying to solve. That's the thing to keep in mind. Again, as I said, deep rabbit hole. Quorums. This is quite simple. Long story short, intersecting sets. If you have set that at some point they have a common process, then you have a quorum. What did you ever say? Doesn't make any sense? Okay. A quorum in a system with n crash fault processes abstraction, for example, is any majority of processes. For example, more than half. What does this even mean again? For example, an algorithm will tell you, like, if F is usually used for failed processes. Yeah, if you have a failure of less than the half of the processes, then I don't remember which kind of quorum this one, or consensus this one is, but sorry. Let's say you have 10 processes and or 11 processes, and 5 of them fail. You still have, you will have a majority of processes that if later, again, 5 more crash, on those 6 that remain alive, at least one knows what happened on the previous round. It's like, as I said, intersection of sets, and there are some properties that say, if more than F are failing, you know, next, keep going. So there are a lot of mathematical theory about quorums. There is a very good book there is a series of books on distributed system. I will tell you some at the end. They are curated by Nancy Lynch, and one is specifically only about quorums. And it's quite, these books are really cool because they are really to the point, and like 100, 150 pages specifically about that topic you wanted to learn about. Consistency. This is the hard one. There is a seminal paper called Linearizability, a correctness condition for concurrent objects, where they define what linearizability is and so on. And usually they take an example of some kind of data structure. In this case, for example, a concurrent FIFO queue. In linearizability, it means you have a particular kind of object, like a FIFO queue, with some semantics like first in, first out. So if I get into the queue and somebody else gets behind me in the queue, one consistency condition can be that I am the first to go out because it's FIFO. That's the thing that is expected from the queue for behaving correctly. Then depending if you want atomicity or sequential consistency or whatever, is depending on the view of which process in the system accessing the FIFO queue or FIFO queue, what is a proper execution of that algorithm. So there are many kinds. There is atomic consistency, linearizability. I will show a small example soon. Sequential consistency, there's another kind, and causal consistency, where you have Afir does a really good job here explaining all this, but basically in sequential consistency, he says, like, if I'm on YouTube, let's say, commenting, as soon as my comments are in order, the ones I'm adding there on Facebook, that's good enough. Then you are at the same time adding your own comments. As soon as you see them coming there to you, that's good enough. But if, in the case of causal consistency, if you reply to one of my comments and I only see the reply and not the original comment or the reply to the reply, then you broke what causal consistency means. I let you to go to Afir. I think it does a way better job than I'm trying to do here to explain consistency models. The point is, when an algorithm or a theorem, like the CAP theorem or whatever, are mentioning consistency, we need to know what they mean by that. It's not, I mean, which of them, or there are way more in a paper that Afir mentions there, or Kyle. Afir has a name, it's called Kyle. Again, jargon, there is a lot of jargon, and we have to know what they mean. So in linearizability, the idea is always about histories of what the process are doing, what is a legal history. For example, here is a registry, and the idea of the legal history is that, where is it? For example, sorry, here, in this registry, the one was written, so here we read one. If we were reading 2 out of it, that's completely inconsistent, because you expect that this order of what's happening in real time, let's say, is respected. This is in atomicity or linearizability. The problem is when you have this kind of concurrent operations, where the start of the operation and the end coincide with the start and the end of another one, is how you decide the linearization point, which is on this real-time line where you have like an omniscient observer is seeing all the operations happening. If you reorder that, those 2, you can do that. Let the write 2 succeed before write 3. OK, that's fine. But read the one on top. They need to keep being consistent. So if this process now managed to read 3 out of it, this also has to read 3 out of it. You cannot make this one concurrently read 2 from back there or something like that. Again, there are more details, for example, in this book and so on. Now, nearly the end of the talk, I'm a book critic for the New York Times, probably. I don't know. This book will be your best bot or the worst. Why? It's called Distributed Algorithms for Message Passing Systems. I'm an Erlanger. I found the perfect book to do distributed algorithms. But at the end of the book, I'm not lying here, the author explains that actually this book never considers failure. So all the algorithms consider a perfect book, a perfect world, sorry. So you can say, flipping tables, why am I spending my money here? If you think you don't need this book, I will say you are not ready for distributed systems. Because this book has a very good explanation of atomicity, sequential consistency, vector clocks, how to build graphs with processes, and many more things. That if you are just learning the basics of distributed systems, they are perfect to get started. Then you know, OK, that's how you solve deadlock detention on a distributed system. Cool, without failures, cool. Maybe there is a path. And the author described that path are all the books he published later. So if you're in his club, basically, you get money. Otherwise, you get poor. Anyway, I recommend this book, if that's what you... Alvaro approves, let's say. Then fault-tolerant agreement in synchronous message passing system. Me, Erlanger, buying books without having a clue. It says message passing system, and it says fault-tolerant, so I need this book, right? But it's about synchronous systems. So here, all these algorithms consider that there is a specific time for running each step, a specific time for message passing, and so on. Not like the real world, at least in the Erlang, let's say RabbitMQ, React, whatever systems. Is useful or not? I guess it's quite useful, but maybe not the first book I will buy. Actually, the books from this series, which is really good, the one I was telling you before from Nancy Lynch, the editor, I wouldn't buy them as the first book on distributed systems. I will buy them after I have some theory that I know what they might be even talking about. But they are quite good because they go straight to practice. Communication and agreement abstraction for fault-tolerant asynchronous distributed systems. So we are getting closer to what we want. Here, the FLP result is discussed, failure detectors and whatnot, and everything is built on top of that theory. It's a really good book. I recommend it. Alvaro approved. Then, Distributed Algorithm by Nancy Lynch. I think this should be kind of some Bible of distributed system instead of this title. They just should put like the Bible or logo on top, whatever that is. Because I was going to make a joke that came to my mind, but I don't know how Christian people is in this country, so I better refrain from it. But anyway, this book is really good. It has a whole first chapter defining all these models I was mentioning before, so you know what you are getting into. It's not like you read a whole book and then, oh, oops, there was no failure modes. No, here you say there's timings, there are assumptions, blah, blah, blah. And then each section of the book, which are quite big, describe algorithms on that section or the other, and so on. Introduction to Reliable and Secure Distributed Programming. This book also has a very good introduction on all these models, failure detectors, whatnot. Has a lot of like a chapter on consensus, another more on uniform consensus, I think, and broadcast abstraction, I think. But the thing is, it talks about secure distributed programming. I think it's the only book, at least from the ones I have, that talks about security in the sense how do you authenticate parties and so on, which most of the books assume the Erlang cookie approach, which is if you have access to the system, you should be trusted. If you don't, if a bad guy comes there to access your system and it screws you up, and like, we told you to keep that cookie secret, right? That's the Erlang way. So this book goes a bit beyond those assumptions. Guide to Reliable Distributed Systems. I present this book because I'm not in the US. Why, you may ask. The author of this book, Kenneth Berman, in the 80s, created a protocol called ISIS. So I'm pretty sure he's in some list, like blacklisted, like why this guy is talking about ISIS. In fact, ISIS was one of the first protocols solving consensus and broadcast and whatnot, but don't Google that because you will get in trouble. But the cool thing, I mean, what he built was used the stock exchange and for airplanes, traffic control and stuff like that. So it's something that was in the last book. So I'm finishing. It was used in practice for real in the 80s, and this was all before Paxos and all this research came about. This book has kind of 10 chapters describing all the evolution of groups membership systems, which need to have consensus, how we reach Paxos, and how we reach the current state of the art. I highly recommend this book just for those 10 chapters. Before it's talking about Corba and other things. Replication, state-of-the-art replication, very good book. Buy it. Last slide, don't kick me out. Finding non-paywalled papers. A big problem is how you get the papers, usually. This may be too obvious, but the problem is that if you know the author, just go to the university page, usually that paywalled paper is there. So sometimes it works, sometimes you need to resort to some other out-of-the-law ways. Conclusion. It's a deep rabbit hole, as you probably saw already. It's computing science where science is still a thing. Here you cannot come up with a consensus algorithm and people will, yeah, cool. No, they will ask you, what about Paxos? What about ISIS? What about this? What about that? Because there is a corpus of research that people respect. That's something I really like about this area. The history of the field matters. And again, read, read, and read. Thank you very much.
I would like to add about finding paywalled papers is that contact the authors if nothing else works. People get flattered and will send you copies. It's a good way of getting
Good to know.
Any questions? We have perhaps time for a very short question.
I have a long question, but it can wait.
Cool.
Then let's take.
Thank you very much.